In the previous three videos, we gave the intuition behind the ratio test and the root test, and we provided proofs of them. But your real analysis book may have given stronger versions of these tests. In this video, we will explain the motivation and arguments for those improvements. And as an exciting bonus, this will nicely motivate one of the most important ideas in real analysis, Lim Sup. No, not that kind of Lim Sup. This is Lim Sup, short for limit superior. And it has a cousin, Lim Inf, short for limit inferior. Anyway, for this video, we will just deal with series whose terms are positive. That will just keep the notation and the explanation simpler. In the ratio test and root tests, you end up taking absolute values anyway, so it doesn't really matter in the end. I'll be assuming that you remember from real analysis class what plain old sup and inf are. It's the Lim Sup and Lim Inf that I really want to motivate and explain. Let's say the first term of our series is some positive number a sub 1, and let's just say that to get the next term we multiply by 0.91, then by 0.901 to get the third term, then by 0.9001, and so on. These multipliers approach 0.9, which is less than 1, so the ratio test works here and tells us that we have a convergent series. Notice that what I'm calling a multiplier is just the ratio of successive terms. I just find it convenient to think in terms of what I do to each term to get the next, so I'm calling them multipliers. Now let's make things a bit more chaotic. What if we interweave multipliers of 0.1? So we start with a positive a sub 1, then multiply by 0.91, then 0.1, then 0.901, then 0.1, then 0.9001, then 0.1, etc. We certainly haven't made anything worse by doing this. The multipliers are smaller than they were before, so the terms are smaller, and we should still have convergence. But the limit of those multipliers does not exist. Our sequence of multipliers oscillates, so the high school calculus version of the ratio test actually gives no information. It seems like we should be able to rescue the situation by noticing that the supremum of all the multipliers was only 0.91, which is less than 1, so it must be true that this series is dominated by a convergent geometric series. So maybe we just want to check the supremum of the multipliers instead. But this goes a bit too far. To see why, let's complicate things a tiny bit more. We'll mix in some multipliers of 2. So to go from the first term to the second term, we'll multiply by 2, then 0.91, then 0.1, then 2, and then we'll proceed as before, alternating between multipliers approaching 0.9 and multipliers of 0.1. Now the supremum of the multipliers is 2, but that value only appeared a finite number of times. Doubling the terms of our series twice should not affect convergence. So we would still like this to pass the ratio test. One way to think of this is that if we look at the sequence of multipliers, it contains two different subsequences that converge to two different limits. Briefly, a subsequence is just a new sequence we get from selecting infinitely many of the terms from the original and keeping the order the same. In our case, you could extract the subsequence 0.91, 0.901, 0.9001, and so on. This is itself an infinite sequence, and it converges to 0.9. Another subsequence is the constant 0.1, 0.1, 0.1, etc. This converges to 0.1. Now it's true that there are multipliers of 2 in our sequence, but they only occur a finite number of times, so they can't affect the limit of a subsequence, since subsequences are always infinitely long. So the largest number that a subsequence can converge to is 0.9, and the smallest is 0.1. We say that the Lim Sup is the largest such limit, and the Lim Inf is the smallest. We could even mix in another subsequence. These are numbers approaching 0.5. Now we said the Lim Sup is the largest number a subsequence can converge to, and the Lim Inf is the smallest number a subsequence can converge to, and 0.5 is neither one of those. But in the special case where the Lim Sup and the Lim Inf are equal, then the original sequence is convergent and has a limit. Now there's a lot we could say about Lim Sup and Lim Inf, and if there's demand for it, we could make a whole video about it. For now, we need a few key facts. Let's say big L represents the Lim Sup of a sequence. If the sequence is not bounded above, then we say the Lim Sup is positive infinity. This is because we can put together a subsequence that keeps getting larger without bound. And the Lim Sup could even be negative infinity in a case like -1, -2, -3, and so on. Here, the only limit a subsequence can have is negative infinity. But if the sequence is bounded above and below, then it must have at least one convergent subsequence. This is a classic result in real analysis called the Bolzano-Weierstrass Theorem. We won't go into the proof, but it's not very complicated, and you probably already learned it if you took real analysis. Let's go back to the case where the sequence has an upper bound. The important fact here is that we can pick any positive number epsilon, and from some point forward, all the terms in our sequence will be less than L plus epsilon. In the language of real analysis, for all epsilon greater than 0, there exists big N, such that for all little n greater than or equal to big N, A sub n is less than L plus epsilon. In other words, we're not saying that the terms are bound above by L. We're not even saying that they're eventually bounded above by L. We're saying that in some sense, the terms eventually get arbitrarily close to being bounded above by big L. Now, why is this? Let's imagine what would happen otherwise. So suppose we have some small number epsilon, and no matter how far out we go, we can always find an A sub n greater than or equal to L plus epsilon. So there must be infinitely many terms above L plus epsilon, and we said that we're assuming the terms are also bounded above. Let's call that bound big M. But this means that we have infinitely many terms in the range L plus epsilon to big M, and therefore there must be a convergent subsequence of just those terms. Its limit must be in the range L plus epsilon to big M inclusive, and this contradicts the fact that the biggest limit a subsequence can have is big L. So to summarize, once we know the Lim Sup of a sequence, we know that for any epsilon, eventually all the remaining terms will be less than the Lim Sup plus epsilon. The corresponding fact for the Lim inf is that for any epsilon, eventually all the remaining terms will be greater than the Lim inf minus epsilon. Okay, now for the main event. Let's see how this property allows us to quickly prove the convergence case for the ratio test. Our new stronger version of the ratio test is as follows. Given a series A sub n, we look at the sequence of absolute values of successive ratios. Take the Lim Sup, and if it's strictly less than 1, the series converges. If the Lim inf is strictly greater than 1, then the series diverges. Notice that if the sequence of ratios has an actual limit, then that limit will equal both the Lim Sup and the Lim inf. So this new test is in fact stronger than the old test. We will prove the convergence part. The divergence case is easier, and we'll leave it as an exercise. Let big L be the Lim Sup of the ratio sequence, which we said is less than 1. We will pick epsilon to be half the distance from L to 1. Then from some point forward, say the big nth term, all the ratios are less than L plus epsilon, which by design is less than 1. This should look familiar from previous proofs we've done. The difference here is that since we only know the Lim Sup, we're saying A sub n is less than L plus epsilon instead of being between L minus epsilon and L plus epsilon. But that's actually all we need for the proof. So if we look at the absolute values of the A sub n terms, the big nth plus first term is at most A sub big N times L plus epsilon. The big nth plus second term is at most the big nth term times L plus epsilon squared, and so on. So our sequence, starting with the big nth term, is dominated by a geometric series whose first term is the absolute value of A sub big N, and whose common ratio is L plus epsilon, which is strictly between 0 and 1. That's a convergent geometric series, and so we're done. Just a quick reminder of why this is better than the old test. Take a series whose first term is 1, second term is 0.9, next term is 0.9 times 0.1, next term is 0.9 times 0.1 times 0.9, and in general alternate multiplying by 0.9 and 0.1. The sequence of ratios bounces between 0.1 and 0.9, so it has no limit. This means that the ratio test fails, but the Lim Sup of the ratio sequence is 0.9, so the new test tells us that the series converges. In the next and final video of this playlist, we will quickly show how to use the same technique to strengthen the root test. And then we will finally answer the burning question of which test is better. Sort of. Make sure to subscribe to receive a notification when it comes out. And giving us a like makes it possible for us to provide more videos like this in the future.